Hello, can you hear me well? I'm not sure if the connection is stable, so let me know if it freezes at some point. So first of all, I would like to thank the organizers for the invitation to speak here. It's a pleasure to participate in this meeting. So indeed, I will tell you how we can bootstrap quantum field theories. And the main idea of this project is to explore the space of quantum field theories using non-perturbative methods. So one usually thinks of quantum field theory as the normalization group flow between two fixed points, one in the UV and one in the IR, described by some conformal theory. And if we're dealing with some weakly coupled theory, we know pretty well how to compute things. We have perturbation theory, we can start from some Lagrangian, draw Feynman diagrams, etc. But if we have strongly coupled theories or want to describe some general quantum field theory, we need some non-perturbative method. So I will be dealing with the bootstrap. Sorry, I want to hide the participants and I can't. Okay, sorry. I will be working with the bootstrap. And this is the idea that starting from some consistency conditions from some very general physical principles, one can describe and compute physical observables, and in practice also put bounds on them. So I will explain in detail how this works for QFTs. And here I will actually be dealing with gapped quantum field theories. So in this RG picture, we will start with some UV fixed point, and then we have a mass gap, so we end up in an empty IR. And one very general motivation for what I'll be talking about is the following. So usually within this bootstrap approach, one considers the CFT and the QFT part separately. So you have the conformal bootstrap to deal with these conformal theories, either in the UV or in the IR. And for these gap QFTs, we have the S-matrix bootstrap. So one very general idea is to try to connect these two approaches. And another idea is the following. So in some abstract picture that I will explain how we can get an actual picture like this, what you get in the bootstrap is something like this, where oh, I need a pointer. Sorry. Is there a way to put the pointer here? On. Okay.
Zoom has a pointer, but I don't know if you share screen. But we can see your mouse, so if you just move your mouse, that does.
You can see. Well,
yeah.
Here, but not in the. Also, when I do this, because I cannot see my mouse.
No, not anymore.
Okay, doesn't matter. Right, so we have this picture where we can get some bounds in some abstract parameter space, so that we have some consistent quantum field theories living, say, inside this blue region here. And usually this space is much bigger than the one we have for known models. So for instance, at this corner on the left, we would have some known model, but the rest of it inside and other special points at the boundary, we don't know what they correspond to. So yeah, we have many more consistent theories than known models. And also, as I will explain with this S-matrix bootstrap, sometimes we have a peculiar UV behavior for these scattering amplitudes. So this leads us to question ourselves, what can the CFT in the UV be? So the stronger motivation is try to understand what are these unknown models that you see with the bootstrap bounds. So it could be that they're maybe unphysical, most of them, but this means we need to impose more conditions. or maybe they are hinting towards a more general class of theories that we should consider. So these are difficult questions to answer. So what I will be dealing here with is with two-dimensional theories, which allows us to have much more control over the analytics and numerics, because usually these types of bounds you get numerically. And there's also this very nice connection to integrable models. So these are models in two space-time dimensions that have an infinite amount of symmetries. And one of the consequences is that any amplitude, say here, for instance, 3 to 3 scattering amplitude, is given by a composition of 2 to 2 amplitudes. So you have this factorized scattering. And this is very nice because you can actually write exact non-perturbative functions for these amplitudes, which is not the case for any interacting theory in higher D. So this is for the introduction. And if you have any question at any point, please interrupt me. You can ask me in Spanish as well if you want. And okay, so this is the outline. We saw the introduction already. Then I will review the S-matrix bootstrap. I will explain this object we call the monolith, what it is. And then I will introduce this mixed bootstrap setup in which one includes into the, it's here. I don't know what it is. Good. So you include some operators into your S-matrix bootstrap setup. And this leads to some form factors, so new observables in the game. And the results we find are bounds on the UV central charges. So it's again trying to make this connection to the theory in the UV. So, and some final remarks. Okay, so what is S-matrix bootstrap? This is the idea of finding a non-perturbative S-matrix that is consistent with 3 general principles: analyticity, which comes from causality, crossing, and unitarity. And this was a very popular idea in the 60s. There was a full S-matrix program in which people were trying to understand strong interactions, but it fell out of fashion for many decades until some years ago. These authors here revived this program. They were very much inspired by the conformal bootstrap. And the new idea here is, instead of trying to find the unique S-matrix for strong interactions, you can put bounds and explore this space of consistent QFTs. So the simplest thing you can do, which is actually what most people do in the S-matrix bootstrap, is to study 2 to 2 scattering. So you have these S-matrix elements of 2 particles as an in state and 2 particles as an out state of scalar particles with the same mass m. And in 2 dimensions, you can see that this amplitude, which depends in the 4 momenta here, is actually a single function of a single variable s, where s is the Mandelstam invariant given here. And this is because you have usually this relation between the 3 Mandelstam invariants, s, t, and u. But in 2 space-time dimensions for this 2 to 2 element, you can set one of them to 0, so that t is related to s by this equation. So you have a single independent variable. Then unitarity tells us that the probability of starting with 2 particles and ending with something else is 1. So in particular, the probability of starting with 2 particles and ending with 2 particles is bounded by 1 for physical values of the energy here. Then crossing tells us that we can actually look at this process as with time flowing in this direction or in this other one. So it relates S and T channel, and T, I remind you here, is just 4 minus S. So it's the simple equation. And then analyticity is perhaps one of the most powerful tools. And it tells you that as a function of the complex variable S, you can only have a certain type of singularities associated to processes like this, when things can go on shell, basically. So, for instance, starting at 4m squared, that is when you can start drawing diagrams like this with two particles in the middle. You have a branch cut. You can have higher thresholds, higher branch cuts here, or when you have 3 or more intermediate particles. Then from crossing this equation here, you get this other cut, this left-hand cut. And then if you have something like bound states, so some cubic coupling to a bound state, you would get a pole at the mass of this bound state in the middle. And from crossing, you get something similar here. So except for these multi-particle thresholds, which you expect to have always, the rest of the pole structure depends on the spectrum of your theory. So for instance, if you consider theories without bound states, then you don't have these poles and just have these branch cuts. So knowing these 3 consistency conditions, you can play a bootstrap game and try to find bounds on certain observables. So the idea is that you would fix your spectrum, basically because this fixes what kind of functions you have here in the complex plane. And then you maximize or minimize a functional of this amplitude S of S. So one thing you could do, for instance, is maximize or minimize the value of a function at this crossing symmetric point. This would be some definition of a quartic non-perturbative coupling. And you can play this game in various different scenarios. Any questions so far? Okay, so what I will tell you about is a generalization of this simplest case, in which you consider particles that transform in the vector representation of On. So we add some global symmetry, On, and now our particles carry some indices, I, J, K, L, that run from 1 to n. And this complicates things enough to have a very rich result, as I will show. So repeating what we did for the simplest setup, now we would have 3 different functions, because we need to take care of these flavor indices. We can contract them in different ways, as I show here with the lines. So this gives us 3 different functions, again, of the Mandelstam invariant S, the center of mass energy, that you can write either in this basis, where these are Kronecker deltas, or in the irreducible representations, which are the singlet channel, antisymmetric, and symmetric. So now instead of 1 function of S, we have 3. And we ask again what are unitarity, crossing, and analyticity. So unitarity is the same as before for physical values of the energy for each representation. Because starting from some representation, you have to end up in the same representation. Then analyticity is again something like this for each representation. Now you can put bound states in different representations, so you can have poles in the singlet, but not in the antisymmetric, or whatever you want. And the tricky part here is crossing. So in this basis of sigmas, it just interchanges sigma 1 and sigma 3, as you see from looking at the process in this direction or in this one, and sigma 2 to itself. But in this representation basis in which unitarity and analyticity are simple, it mixes different channels. So there is this matrix here that depends on n for On. And this gives enough constraints to make the problem very rich. So something that we did was to study the space of all possible amplitudes, SA of S, for theories without bound states. And to study this space, what you can do is maximize functionals of this form, where you have the 3 different channels with some coefficients. You change the coefficients, and in this way, you scan this space. It is actually an infinite dimensional space because you have this continuous variable S. So something you can do is plot subsections. And these subsections, or this space, is what we call the monolith. So this is a 3D plot of what the space of these amplitudes without bound states can be. The axes here are the 3 different functions, sigma 1, sigma 2, sigma 3, at a given energy. You can do it at different energies. It's the structure remains more or less the same. But something very interesting is that you can see some vertices, some edges, and you can ask yourself, what are these vertices? They seem to be special. And indeed, you see that some interesting theories lying at special points on the boundary. So I will actually be discussing mostly this 2D subsection, where you evaluate at the crossing symmetric point, this 2m squared. And you see that there are integrable theories lying at special points of the boundary. So for instance, these black dots here are free theory, where the S matrix is just +1 for all channels for the free boson, and -1 for free fermion. Then this blue point, which is actually a vertex, as you can see, some edge ending there here, is the ON nonlinear sigma model, which is also integrable. And there you have a non-perturbative expression for the amplitude, written in terms of this rapidity theta, which is related to the center of mass energy squared S in this way, and where N enters here in these gamma functions. And there's another answer, I should have said this before. There is a symmetry of changing S to -S. Basically, if you maximize in one direction or minimizing the other one, you always have this symmetry because you can just change the signs of all 3 representations at the same time, and that's as valid as before. So the actual physical here of the nonlinear sigma model is this one here with a plus sign. But if you switch the sign, you also get a point at the boundary. It's a non-perturbative S matrix, but you don't have a known theory for it. And then there is a third integrable point given by these green dots, which we call periodic Yang-Baxter. And it's similar to the nonlinear sigma model, the S matrix, but it has some infinite product of these gamma functions. And we call it periodic Yang-Baxter because it satisfies this property that in the rapidity variable, it is actually periodic in real theta. So in some parametrization of energy with a given period that depends again on N of ON. And with this optimization procedure that we do numerically, you not only get this plot here, so this bound, but you actually get the full S matrix at the boundary. So the function saturating these bounds. And you can explore what it looks like in the complex S or theta plane. See if you have resonances, which would be zeros instead of poles in this complex S plane. So we see that generically the theories at the boundary have many resonances, actually infinites of them. And there is some emergent periodicity as for periodic Yang-Baxter, where the period here depends on where you are at the curve. And this sounds very strange because it's telling you that the amplitude is periodic in some parametrization of the energy. So it leads again to this question of what's the UV of these series. And then some other generic properties that this amplitude saturate unitarity for this 2-to-2 scattering element, which means there is no particle production. You don't get 2-to-4, 2-to-6, etc. And this is okay for the integrable theories because, as I said, all these amplitudes of n to n particles you can factorize in terms of 2-to-2. If the theory is not integrable, this doesn't make sense for all energies, only at low energies. But we expect that what we're finding is actually a good approximation to the true thing. Okay. So this is what we find for this.
There's a question.
Yes.
Pedro, you want to go ahead?
Okay, sorry, one question. Maybe you can postpone it, but is there or are there any points that we know of inside of the drawing? The asymmetrics, I mean.
Yeah, so known, okay, there are several answers. The first one is that inside you don't have a unique S matrix, so you can have many different things that in this subsection, which you can see as a projection of this infinite dimensional space, lie in the middle. So any point here inside could be described by many different S matrices. However, there are ways to go inside. I can give you one S matrix that is inside. So yeah, I don't know if you're familiar, but
no, I am not. But maybe I can
called...
postpone this discussion for you to have time to finish your talk. So I come back later on this. Thank you.
Well, listen, but yeah, for instance, Gordon theory, which is an integrable theory as well, could be inside a theory without bound states. So you can go from, say, free theory to minus free theory easily, and this would be Gordon.
Thank you very much.
Yeah. More questions? Okay. So the last thing I want to say in this review part is that even though I'm not explaining how to get the bounds numerically, I want to say this thing. There are two approaches to get these bounds. One is called the primal, which is in this left-hand side. That is the one I talked about. And in this primal approach, you explore the space from the inside by constructing amplitudes that actually are already analytic, crossing, and unitary. So you get like maybes, or yes. You can get something that satisfies all these conditions inside. But there is another approach called the dual approach, in which instead of maybe you say, no, outside of this, you cannot have an amplitude that is consistent with these principles. So it's basically using some Lagrange multipliers. This gives you a complementary approach to finding what would be the optimal bound here in the middle. So basically, if you have a larger ansatz for your amplitudes, you can get to the optimal bound in one direction. And if you have a larger ansatz parameterized by this Nmax for your dual variables, you approach from the other one. And this is important conceptually because it gives you rigorous bounds. That means, again, that outside of these red lines, for sure, you cannot have a consistent QFT. It's also faster numerically, but the primal is still very useful to understand the analytic structure of the amplitudes. So, okay, now we go to the second part, which is adding some operators that will allow us to tell about the UV CFT. So the idea is to add the existence of a given operator into the S-matrix bootstrap setup. And this was proposed in this paper here. And the idea is actually very simple. So before we were dealing with two-particle in and out states. So we have two different states, this two-particle in or out. And now we're considering a third kind of state, which is given by the operator acting on the vacuum with some Fourier transform. And now unitarity will be the fact that this matrix of inner products is positive semi-definite. So for instance, if you restrict it around here, which is the two-particle in and out only, you recover unitarity of the S matrix. But now if you include this third type of state with the operator, you get two different observables. One is called the form factor, which is this mixed state between the operator acting on the vacuum and an out particle state, or in with CBT. And it appears here in this, when you have psi1 with psi3 or psi2 with psi3. And now for the two psi3 with psi3, you get something called the spectral density, which is a two-point function of the operator, again, Fourier transformed. So the positive semi-definiteness of this matrix, big matrix here, there's this Sylvester's criterion which tells you that the principal minors of the matrix are positive. So it's equivalent to say that the determinant of this blue matrix is positive. This gives you unitarity. The one for this red one gives you this condition between the spectral density and the form factor. This last one gives you that the spectral density is positive, which you know as well. And then the big determinant, the 3x3, gives you a more complicated equation with all three pulses. So what happens if things are saturated here, as we were seeing saturation of unitarity when we're doing just S matrix bootstrap? What you get is that all these observables are saturated by its two-particle contributions. So again, this 2-2 S matrix element is given, saturates unitarity, so it's equal to 1 for physical values of the energy. All of this is for S physical. Then the second condition tells you that the spectral density is proportional to the form factor squared, which you can think if you include here the sum over all in or out state, you see that you can write the spectral density in terms of two-particle plus four-particle form factor, etc. So if you saturate this inequality, your full spectral density is given only by the two-particle contribution, because this is the two-particle form factor. And finally, but very importantly, you have this Watson's equation from this third condition. If you saturate unitarity and also have this other condition, you're left with this equation that relates F and the imaginary part of the form factor to the amplitude. So this is called Watson equation, and it's used in integrability. There's actually an integrable form factor bootstrap in which you write the two-particle and also the n-particle form factor from the S matrix. So, okay, this will be our new unitarity equation for when you have some operator into the game. So going back to our
sorry,
ON setup.
Can I ask you a quick question?
Yes.
On the previous slide?
Sure.
So the form factor, well, I guess the second inequality that you have for the spectral density and the form factor, I guess I could understand it as from the saturation as if you put a complete set of states and the leading order would be the 2-2 scattering, and then any corrections will just make it larger. Like if there's particle production, it just increases the spectral density. Is that the idea? Like if instead of having just the two-particle Hilbert space inserted, in a complete set if I include like 3 particle state?
Yeah. So, okay, there are several points. The first is, yes, it's what I tried to explain too fast. But indeed, this is the definition of the spectral density. You can insert the complete basis here of 2 times 2 and 3 and 4, whatever. So you can write the spectral density as F2 plus F3 plus F4, etc. So indeed, usually you will have that row is bigger than F2 because F3, F4 are non-zero. They are zero only in free theories. So actually for integrable theories, even if you don't have particle production, the form factors are not zero. I guess you can also see it from the fact that it's not that you don't have 4 particle states. It's just that the 4 particle states, well, if you do this inner product between 4 particle in and out, you can see it as a factorization of 2 to 2. So it exists.
Okay.
Going back to this picture of this scattering of 3 to 3, this amplitude is non-zero. It's just that it's given by sequences of 2 to 2 scattering.
I see.
Well, thanks for the question.
Thank you.
More questions? Okay, so going back to our ON scenario, we would have 3 different matrices B, depending on the irreps we're using. And the operators we will use are the stress tensor, or well, the trace of the stress tensor, which talks to the singlet channel, so it's a singlet of ON. That gives us these 3 different matrices where we have a bigger 3 by 3 for the singlets, and the antisymmetric and symmetric are as before. We just have the amplitudes. And we will also use the ON current, some scalar made out of it. And the currents are in the adjoint of the group, so they talk to the antisymmetric channel here. So you would have a bigger 3 by 3 matrix for this channel if you include the ON current. And why do we use the stress tensor and ON current? Well, in a sense, it's very natural because we're dealing with QFT. We expect to have a stress tensor, and with ON, so we should have a current for this symmetry. But the important thing is that since these are conserved currents, they lead to some sum rules. So famously, the one for the stress tensor leads to the C theorem. So from this conservation, you can derive this equation here, where you have the difference between the UV and IR central charges. I remind you, I'm dealing with gap theory. This is actually 0. And this central charge C is related to an integral of the spectral density of this operator, the trace of the stress tensor. And this C is what appears in the 2-point function of the stress tensor in the TFT here in the numerator. And for the ON current, there's a similar K theorem, perhaps less well known. So you can write a very similar condition where you have the central charge K in the 2-point function of the currents in the CFT like this. And it's given by some integral of the spectral density of this operator here. So this is very nice because it allows us to have access to these central charges in the UV from what we're constructing here, these 3 different states. So our new bootstrap problem will be to minimize the central charges subject to these more general unitarity conditions. So we do this numerically. It's actually kind of hard to do, but I will show some plots and results. So this is work in preparation with Miguel Correia, Alessandro Georgoudis, and Vuignier. And let me show you some pictures. So for instance, if we minimize C, the central charge for the stress tensor, the global minimum on this monolith that I was showing before sits here. This is for n of ON equal to 7, but you can do it for various n's, and you see it's always on this line here. And you can also minimize on the full surface here or in some sections. I will show first. So for instance, for this section, connecting the nonlinear sigma model and its minus part, you get something like this. So with this dual approach, which is the rigorous bounds, you get something here, so that allowed values for C are in the shaded region. For the primal, you get something a bit larger here with the dashed. But it seems to go to some constant value here. And then what happens with this other section connecting these weird integrable models? Here you see that the bounds actually diverge close to the boundary and go again down in the middle and seem to diverge again. So for these endpoints, actually, we know the fullest matrix, it's integrable. We can compute actually analytically what this two-particle contribution to C is. So you can get these points I drew here analytically, and they are finite for the nonlinear sigma model, as they should be, at least for one side. And for periodic Yang-Baxter, you get infinity. So now the question is, which matrices give infinity, decentral charge infinity or finite? What are the conditions? And also, having the central charge going to infinity could be a way of saying maybe they are unphysical or incompatible with the assumptions I'm doing now. And I want to show first another plot. This is a temperature plot for the full surface. For n equals 7, again, the minimum central charge is somewhere around here. And so you see it's like a hammock. It has some minimum in the middle and grows at the boundary. And okay, so about numerics, you can take from minutes to hours per each point using some program for positive semi-definite matrices, SDPB in the cluster. So yeah, it's complicated to get these plots, but you can do it. There are rigorous bounds. And finally, these dashed lines are actually the points at the boundary where we know the S matrix, and we know that C should be infinity. So let me see how I'm doing with time. Okay, I will go very fast in this part. But there's a way to understand which S matrices give rise to infinite central charges. And this is using what is well known in the integrable community. So you can construct the form factor and the spectral density from the S matrix when you have this saturation of constraint. And then what you want to do is study possible divergences of the sum rule integral to see which S matrices give you infinite central charges. So if your constraints are saturated, you can write the S matrix as a phase for physical values of the energy. Then you have this Watson's equation, and rho is given by F squared. So the idea is to write the form factor as the product of two parts. One that is fixed by the S matrix from the Watson's equation, and some freedom here where this function V is real and meromorphic. And you can use this freedom to try to make C or K converge. So yeah, basically this alpha function here is related to the arguments of the S matrix. So this part is fixed from the S matrix. And for the B, you can use the fact that this other function is bounded because this phase goes from minus pi over 2 to pi over 2. So these bounds on alpha let you know how big or how small you can make B. And the only thing I want to mention here is that at infinity, B can only grow linearly with the energy, or S. So if it grows faster than this, then this sum rule diverges and C is infinity. So now what we found, I will go fast because I'm running out of time, is the following, that I should have written this differently, sorry. There are something we call dangerous points in the S matrix, which is whenever the S matrix reaches -1 with a given slope for the imaginary part. Why? Because this gives rise to a discontinuity in this alpha function, which gives a 0 or a pole in B. And if you put too many zeros versus poles in this freedom of the function B, you basically can spoil the convergence of the integral because you're not satisfying this condition. So basically, if the S matrix passes through -1 with a given slope of the imaginary part more times than when it passes -1 with the other imaginary part, then your central charge can diverge. So there's also a similar thing for K. But this, for instance, explains why the Bredigan-Baxter has C equals infinity. Basically, if you plot this function in terms of theta or S, you see that it has infinite dangerous points, such that this condition here is never satisfied, so you have C equals infinity. So this is always the case for all these points at the boundary with the dashed line. So here. But interestingly, even though the S matrices are periodic here, they don't have enough dangerous points, so C is finite. So you still have periodicity, but finite C. Okay, now we'll show some plots for K. If you do the same for K, the central charge for the ion currents, you see that the global minimum is close to the free fermion. You can draw different sections. So for instance, this one between free fermion and free boson goes from K equals 1 to K equals infinity. For those of you that know about the bosons in 2D, this would be the non-compact boson. So it's fine. You can also do this temperature plot. Now it has some minimum close to free boson, and it grows towards free fermion, and it grows towards free boson. These 2 points here are where we have K equals infinity. And it's the same as this point here. And the last part I want to show is what if you do both at the same time? So you say fix some C and minimize K, or the other way around. So if you do this, it's getting some pure CFT bounds. So these are just UV CFT quantities in and K. And you get something like this. So the bigger picture is more like a corner. If you remember, I said C, the minimum C is around 2 point something, and the minimum K is close to 1. So as you go from this minimum C, which was sitting here in the monolith, towards the minimum K, here you do this inside. Oops. And here I'm showing both the primal and dual points as you increase the size of your ansatz. And then this black line is some simple extrapolation to when you have infinite variables. So the allowed values for C and K are in this gray shaded region. And something that might be familiar to some of you is K as the level of some affine algebra. So when you do have this affine algebra, you can write the stress tensor in terms of the Owen currents with this Uehara construction, as you do for Vesuminovithan theories. And this gives you a relation between C and K, where you have some parameters of the group. Here is just some function of n. And this lies here inside in this purple line. And you expect that compact CFTs would lie to the right of these bounds here, but we don't have any reason to impose a priori that our CFT should be compact. So you see that it's much larger here, this allowed space. And actually free boson sits somewhere here on this other left-hand side. So you can see this as a pure conformal theory bootstrap. And now I'll pass to the final remarks. So I'll show you first how you can get the space of consistent QFTs for these 2D theories with no bound states and some global symmetry ON. And this new part is about getting bounds for the UV central charges, C and K. And the last plot I showed, you can see it as towards a classification of ON CFTs, because people know how to construct some of them for specific, with some specific conditions, but a full classification, to my knowledge, is not known, even for 2D CFTs. We also understood what are the necessary conditions for these S matrices to have infinite or finite UV central charges. So curiously, it's not about periodicity, but these dangerous points. And also, we saw that most of the monolith is compatible with all our assumptions of unitarity and some CFT in the UV. And this gives some tension because there are some hints that the UV behavior of this theory should be outside of the real unitary CFT we're used to. We know this from some studies for integrable models and some deformations of statistical models like ON critical models. So something we would like to do is to try to extend this setup to include more general kind of CFTs like logarithmic or complex. And here also I showed you how we can study the big space of QFTs and try to learn about the UV, but you can also try to fix the CFT by, say, fixing the central charges and bound the IR observables, as was done in this paper for Eaton field theory. So if you have a particular theory in mind that fits in this space, we can also study it more precisely. And yeah, that's it. Thank you very much.
Great, let's thank Lucia for the very nice talk. And do we have any questions?